This is podcast 5.5 for chemistry. It's going to be our last podcast in this unit. And we're going to talk about how you can write ionic and net ionic reactions. And this is for double replacement reactions. So the first thing we need to recall from the last podcast that we watched is that when ionic compounds go into solution, they dissolve or they break up into their separate ions. And here's an example using sodium chloride. These would be the chlorine ions, and these would be the sodium ions. So chloride and then sodium. But that's how they would look. It's a salt crystal right there, and then you have all these water molecules on the outside. The water molecules, remember, this would be the oxygen, and then the hydrogens are the two littler atoms right there. So if we were to take this and watch it over time, what we would see is that the water would come in and it would start breaking this crystal apart. And you can see that right here, the chloride ions are being taken away, broken off, and here's the sodium ions. So the chloride ions are attracted to the positive hydrogens on water, and the positive sodium ion is attracted to the negative oxygens on the water. And the oxygens, or not the oxygens, the waters come in and just kind of keep breaking this down into the individual atoms until all we're left with are a bunch of sodium ions and a bunch of chloride ions floating around in water. And that's why we talked about that in class quickly about this is really what these ionic compounds look like when you have an aqueous solution. So anything that's aqueous, that really means it's in ions. It's broken down into its ions that make it up. And what we're going to do is we're going to take those ions and we're going to form, or we're going to write these ionic and net ionic reactions. So here's another example using silver nitrate and sodium chromate. What you can see, the two separate solutions, because they're both aqueous, they're split into their ions. So silver nitrate aqueous really is silver ions and nitrate ions. And then on the other side, in the other solution, we have sodium and the chromate anions. And because they're both aqueous, they're both split into their ions. When we pour those two together, though, we end up with this solid down here. And if you were to use your solubility table, it's either going to be sodium nitrate or the silver chromate. That's your solid over here, because that's what happens in these double replacement reactions. But you would be able to tell that the sodium nitrate stays in solution. The ions are still here and you can see them. Here's a sodium ion, here's a nitrate anion, and they're still floating around in the water. What happened though is the silver joined up with the chromate, it became insoluble, and that's what we're seeing as kind of this orange colored precipitate coming out of solution. So this is just a refresher on what happens in these double replacement reactions, which we sometimes call precipitation reactions. Okay, so the first step that we have with writing these net ionic equations is to write the balanced molecular equation. That's what we've been doing when we've predicted the products of these double replacement reactions. That's nothing new. This is the same thing that we've already done. So just doing what you already know using the solubility table, predicting products, writing it out, balancing it, that's the first step. The second step is where you write the complete ionic equation. And this is where you're going to take all your aqueous compounds, so anything that you put an AQ after, you are going to split up into its ions. So for example, if I had potassium chloride, I'm going to actually show that as K plus the Cl minus. So you're going to show the charges and you're going to show the number of them that you had. So this means if I had sodium sulfate, you need to show that as 2 sodium ions, AQ, and 1 of your sulfate anions. So you're splitting these up into the number of ions, including their charges, and also still putting the aqueous after it. So step number 2, you need some room. It takes up a lot of space. Big things to remember: do not split, if anything, that's a solid or a liquid. So if you have water with the L after it, it stays as water with the L after it. Don't split it up because it doesn't do that in solution. They stay together as molecules. The same is true for your solids. They don't split into their ions. That's the whole reason we see those precipitates when we put these solutions together. The solid comes out, we're able to see that, don't split them up. Subscripts become coefficients. That's what I was doing down here where there were two NAs and I brought it up to be a coefficient in the front. Then after that, you're going to write the net ionic. So we have the balanced molecular equation, the complete ionic, and then the net ionic. The net ionic is where you're going to cancel out spectator ions. Those are ions that exist on the same or on both sides of your reaction. And that might be a little more clear once we do an example with this. So I just have two examples to do with you. The first one is example problem 1, and we've already been given the balanced molecular equation. So we don't have to do anything to write that. It's been given to us. All the states of matter are included here. We're going to focus though on writing the complete ionic and the net ionic. So for the complete ionic, this is where we're going to take anything that's aqueous and we're going to split it up. So I'll start here. Barium, when it's an ion, has a charge of +2. So it's Ba plus 2, and I put the aqueous sign after it. Plus, I have nitrate here, and there are 2 of them. So 2 nitrate ions, and they're also aqueous. Plus, moving on to this one, we have nickel, and this nickel must be a +2 charge because sulfate is a -2. So this would be nickel +2, and I'd put the AQ, plus I have the sulfate anion, and that takes care of all my reactants. Then I move to my product side. You need to be careful on your product side not to split up your solid that you are given. So I'm going to do the nickel 2 nitrate first. So nickel again, +2 charge, aqueous, and I'm going to move down here, plus 2 nitrates, plus barium sulfate stays as is. Because it's the solid, it doesn't split up. So that would be my complete ionic equation. It does take a lot of room, and yes, you have to put aqueous after each of these ions. It's just how it's done. Then though, to move on to the net ionic, you cancel out those spectator ions. So spectator ions are ions that show up on both sides. If I look then, I have barium with a +2 charge on this side, but I don't on this side of the arrow have any barium with a +2 charge. I have barium here, but it's with the solid, so they're not the same. I have 2 nitrates. I also have 2 nitrates on the product side, so those are spectator ions, they cancel. And then nickel is here, and I also have nickel there. And then just to double check, the sulfate is an ion on this side, but it's in a compound on this side. So I was able to cross out the nitrates and the nickels. Those are my spectator ions. So the nitrate and the nickel were the 2 spectator ions for this equation right here. Then for the net ionic, I just rewrite everything I didn't cross out. So it's Ba plus 2 plus the sulfate ion gives you the barium sulfate solid. And you should check that the ions you're putting together over here should produce the solid that you want on the product side. So if I put this and this together, I will end up with barium sulfate. And that's what they are. I don't think they're necessarily hard. The problem is that people forget to split everything up, or they forget to write like the 2 out here, or they'll split everything and not leave the solids intact. So you just need to be really careful when you're doing these, following the rules. Like for spectator ions, they have to be identical on both sides, but we're going to do one more together. Okay, so we're going to do this one again, and this time they gave us the 2 reactants, and we're going to have to figure out the products. So strontium hydroxide, if you use your solubility table, you're going to see that it's aqueous. And chloric acid, because it's an acid, we know that it's aqueous also. To figure out your products though, the strontium, this is the formula for chloric acid. So the strontium is going to go with the chlorate. This is the chlorate anion, and if you look that up on your solubility table, it's aqueous. and then the hydroxide is going to go with the hydrogen. And if you look up hydrogen hydroxide, you're going to see that it's water, which is a liquid. So this is a good reaction to go because we're getting one of our products as a liquid. So we have strontium hydroxide, which is aqueous, plus our chloric acid, ClO3, gives us water and strontium chlorate. And then to balance, I'm going to have to put a 2 here and then a 2 here. So there's our balanced molecular equation. The next thing we're going to do is write the complete ionic. So I'm going to take everything that's aqueous and I'm going to split it up into its ions. So we have a strontium ion plus 2 hydroxide ions plus 2 hydrogen ions plus 2 chlorate anions. That 2 is going to go to the hydrogen and to the chlorate, plus 2 waters, and those stay intact because they're a liquid. And then you have your strontium, again with the plus 2 charge, and the 2 chlorate ions, which are also aqueous. So that one's kind of spread all over the world right there, but we can still pick out what goes where. Now you're going to look for spectator ions to cancel. So the strontium I see on both sides, and I also see the chlorates on both sides. So my last step is to write the net ionic, and that's where I take the 2 hydroxides that I'm left over with, plus the 2 hydrogen ions, give me my 2 waters. And just like you should do with your regular balancing equations, because these are all 2's, I can reduce them down. So it's going to become a hydroxide ion plus the hydrogen ion gives you water. So that would be your final net ionic right there. Okay, so we have the balanced molecular, we have the complete ionic, and we have the net ionic. We'll do practice with a few of these in class. They do take up a lot of room and a lot of time, but you can do it. Just don't forget to keep your liquids and your solids together, never split them up. So that is it. Make sure you still have your solubility table so you can use it, and we will do more practice with these in class.